Okay, here we are. Welcome back, gang. This is hopefully our last meeting in this online setting for Calc 2 honors this semester. I am supposed to be cleared. They told me I'm cleared to come back to campus on the 15th or the 16th, and the contact tracers would let me know because they couldn't decide which date to use as my start date. But I'm hoping that means that either way, Wednesday's class will be in person. So that's good news. Happy Valentine's Day, of course. If you got something special, don't forget to buy them some chocolates or write them a nice note or any combination of those sort of things. Last time we were talking about improper integrals, and we saw a handful of different ways that an integral measuring an area could maybe fail to make sense. Could either fail to be finite in the sense that that area turns out to be unbounded, or could fail to be kind of well-defined in the sense of like the integral of sine x just done from 1 to infinity or 0 to infinity. Today, we're going to continue exploring that concept of convergence, but we're going to start talking about a completely different set of objects. And what we'll see is that after we get through this section, 11.1, which is kind of going to feel like a weird change of pace, we're going to introduce objects built out of these things called sequences, which are very, very similar to type 1 improper integrals. So this is MAC2312, section 0H1, which is Calc 2 honors. And today is, 2/14/22. The date today is an interesting date. So one of the things I used to do when I first met my wife was write her little notes that would take the day in this, month, day, year format and form an integer out of it, 21422. Give the prime decomposition of that and then try to find some cute, interesting fact about that number, right? Like, is it a sum of two squares or is it something like that? This is a semi-prime with a very, very large second factor. So this is 2 times 10,000, what was it? I've closed it. 10,711, which is quite rare, right? Primes are somewhat rare, semi-primes are somewhat rare, but even rarer than a semi-prime is a semi-prime where one of the factors is very small and another factor is very large. As you go up in the ladder, that sort of thing happens less and less. So this is a fun thing about this guy today. We're going to introduce sequences. Which is section 11.1. I know everybody is anxious to get their tests back. Obviously, since I'm not here, I can't hand you the piece of paper. But today, after my office hour, I'll be putting the grades into the Canvas gradebook, so you'll be able to see them there. And then for the actual feedback, the physical papers, I'll have to wait until I can hand them back to you in person. I think there were 3 people who took the test either in the G25 testing center or the big open lab in building N. I haven't been able to recover those because I'm not allowed on campus. So those tests will probably have to wait. But on Wednesday, when I come back to campus, I'll collect those tests from the testing center, and then I'll try to grade those as quickly as possible by the end of the week. So everybody's kind of on the same page moving forwards. Okay. The word sequence is a word that we all have some familiarity with. We can have a sequence of pencils. If I line up a bunch of pencils on the desk, there's a first pencil, a second pencil, a third pencil, and so on. You'd have a sequence of people or a sequence of actions. In mathematics, a sequence. I'm going to give 2 definitions, and one is quite formal, and the other one is quite informal. And the first thing I'm hoping to do today is get to a place where we can see the formal definition and the informal definition is really saying the same thing. So formally, a sequence is a function whose domain is potentially a subset of the natural numbers. Okay, and the range or codomain could be anything. Could be pencils, chairs, people, numbers. But the important thing about a sequence, what makes a sequence is that it's a function or a pairing, a rule for pairing objects between two sets, right, a function, where the domain, the collection of inputs, is discrete, right? And the classic example of a discrete ordered set is the natural numbers. Less formally, a sequence is an ordered list of objects. And again, those objects could be anything. For us, at least most of the time, they will be numbers, right? Because we generally study functions that take in numbers and spit out numbers. But like I said, you could have a sequence of chairs or pens or students. One other very important type of sequence is sequences of functions. So you have a first function, a second function, a third function. I could have a list of functions. And this is usually something you encounter when you start to talk about approximating functions. So you can approximate complicated functions with a sequence of simpler functions. Very, very important stuff in analysis. And when we talk about Fourier series, we will have no choice but to dive a little bit into this concept of a sequence of functions. But as we get started here, the first few hundred examples we will encounter, the output from this function or the objects in this list will be numbers. And then there's some notation. I've always kind of wondered historically why this notation is the way it is. And if you're still looking for a cool honors project topic, exploring the notation behind sequences, I think would be a cool one. Instead of writing let me see, so if we use the normal function notation, f of 1 would be the first output, right? The output associated with the input 1. And most people start the natural numbers at 1. Some people start them at 0, right? If you study in France or some other parts of like Central Europe, they consider 0 a natural number. But we'll start at 1 most of the time. F of 1 would be the output from the function f at its first input, because the inputs here are just the natural numbers. F of 2 would be the next one. F of 3 would be the next one, and so on. But instead of writing f of something, we tend to write f sub something. Where you use a subscript instead of the parentheses, right? And it means exactly the same thing. It means this is the first thing in the list. This is the second thing in the list. This is the third thing in the list. And also, we usually use letters at the start of the alphabet. To name sequences rather than F or G or H, like we do with functions, right? For reasons that do make some linguistic sense, we usually use the letter F to denote a function, right? Like F of X, probably because the word function begins with the letter F. But when we're talking about sequences, instead of calling them F and then thus, F1, F2, F3, usually if we're talking about a sequence, we would call it like A1, A2, A3, that's the standard sort of way of writing these. So this would be the first three terms of the sequence A. If I wanted to refer to the whole of the sequence rather than just one term, so this, let me add some language. This guy here would be called the first term. And well, this one be first term. We call this guy the second term. We call this guy the third term. Right, so the actual outputs, the things in the list, the numbers that the sequence spits out, those are called the terms. And because this is an ordered list, there is a first one, there is a second one, there is a third one, and so on. So we refer to them as terms, and you can identify the term you're talking about by the index. If I wanted to refer to the sequence that makes up the digits of pi, right? I could do that, and the first term would be 3, the second term would be 1, the third term would be 4, and so on, right? 3.141592, blah, blah, blah. One last bit of notation here. If I want to refer to the whole sequence at once, rather than the individual terms, we write curly braces AN usually. And this is what you'll see in the textbook. And depending on the degree of formality, you might see a little n equals 1 to infinity here, or maybe just n equals 1 to indicate, where the sequence starts. Because like I said, sometimes we start at 0, sometimes we start at 1. There's nothing to stop you from starting at 2 or 5 or 10 if you want. So this notation just tells you what's the first input for that sequence. Does that sequence start with a first term or a second term? Or maybe does it start with a 0th term? There are other notations for this. Some people use a soft parentheses rather than the curly brackets, but in calc class, it's pretty much always curly brackets. I'd like to just look at a few concrete examples to get us a little bit comfy. And then we're going to look at the graph of a sequence. And we're going to ask ourselves the question, well, what sort of calculus operations can you do with these things? Because it's not immediately obvious. We need more time to write. We're good. That's all well and good. I could say let and maybe I'll start this one at 0, from 0 to infinity. Be the digits of pi, which we know is 3.1415926, blah, blah, blah. And just write out the first 5 terms. There's a thing here to pay attention to, of course, right? We chose to start this sequence at the index n equals 0. So the first term we could write down would be A0. The next term we can write down would be A1, and we'll keep going like that. So the very first digit of pi would be A0, and that's the number 3. So A0 is equal to 3. The next digit of pi is 1. So A1 would be 1. A2 would be the digit of pi that comes right after A1, which is 3.14. A3 would be the digit that comes after the 4, which is another 1. And then A4 would be the digit that comes after that 1, would be a 5. And since we started at 0, this is the first 5 terms. You can do this with any decimal number, right? You can take any decimal number in the world and write down the sequence of digits. And well, some of the most important developments in mathematics in the early 20th century came from expressing numbers like this. Rather than thinking about this number as like a point on the number line or a length or something like that, thinking of it as its sequence of digits, perhaps times some order of magnitude. Gerhard Cantor used this way of thinking about real numbers in order to prove that the infinity of real numbers is strictly larger than the infinity of natural numbers, meaning there's no one-to-one correspondence between the set of all natural numbers and the set of all real numbers. One of the things we often like to do, given a sequence, is to find a formula for the nth term, right? If I can give you like an algebra formula to tell you what A10 or A50 or any AN would be in terms of the number n, that would be really nice. Some mathematicians who are trying very hard to do this sort of stuff right now are the Borwein brothers, Jonathan and Jacob Borwein, very famous mathematicians who work between the University of New South Wales and UF. They travel back and forth, and I think they also have one of them, I should say had, I think Jonathan passed away last year, had offices in Canada as well. But yeah, finding a formula for the nth digit of pi, that's a big deal. If you can do that, let me know. You get a Fields Medal for sure. So sort of the classic problem is to try and find a formula for the nth term of the sequence which begins, and I'll do like 2 of these, I think, maybe 3. Begins with a list of numbers. So right, these like Facebook what comes next things really are deep mathematics problems if they're challenging enough. So let me break this down into a few parts here. The first guy, we'll say the sequence is AN. And I won't specify a starting index just yet, but let's say that the first term here is 0, and then 2, 4, and then 6, and 8, and then 10, and so on. And for part B, let's call the sequence Bn, and I'll just list out. I can even write it like this. You'll see this notation in the book, so I might as well share it with you. Sometimes when you see a sequence written out like this, they'll put it in the curly braces, and so this is the first term, the second term, the third term, and then we're referring to the whole sequence. For Bn, let's do 1, 3, 5, 7, 9, 11, and so on. And the ... means continues in this fashion. Right? That's called an ellipses, and you've seen me use them in some places, but we'll be using lots and lots of ellipses throughout chapter 11. And let me throw a third one in here. There's one that kind of fits nicely in this. Cn. So let's do 1, 2, 4, 8, 16, 32. So what I'm looking for in each of these is an algebra formula, right? Just write an equals blah, 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 you know, and maybe it's n squared or 1 over n cubed or something like that. Sometimes it can be very helpful to characterize the terms of the sequence in language. So how would you describe the first sequence, an? That is the sequence of what? What are we listing there?
Even numbers.
Yeah, it's the list of even integers, right? What makes an even number even? Many good answers here. Just tell me what comes to mind for you. I'm not looking for something specific.
That you get an integer when you divide it by 2.
Yeah, I like Ian's answer there. That's a good one. Divisible by 2, right? You get an, if you divide any of these numbers by 2, the result will be an integer. Yeah, 0 divided by 2 is 0, 2 divided by 2 is 1, 4 divided by 2 is 2, 6 divided by 2 is 3. There's another way to say that, right? If we write down the equation that says, you know, n is divisible by k, we would say n is equal to k times something else, right? Where that something else is an integer. So 0 I can think of as 0 times 2. 2 I can think of as 1 times 2. 4 I can think of as 2 times 2. 6 I can think of as 3 times 2, and so on. So an here, this will allow us to write down a formula. The nth term, if I wanted to know what like the 5th even number is, well, the kind of 0th even number is 0 times 2. The first even number is 1 times 2. The second even number is 2 times 2. The third even number is 3 times 2. So this is n times 2, or just 2n. And if I choose to write the formula this way, n begins at 0, right? Because in order to make this match up, that first value of n needs to be 0. So we could say here that this sequence is an is 2n, where n is 0, 1, 2, and so on. Or if I was writing in the curly bracket notation, I would put an n equals 0 down here and an infinity up there. Okay. Any questions on coming up with this answer, that an is equal to 2n? This will be a convenient fact for us in the future, right? That you can write the nth even number as 2n. What about the sequence bn?
Two n plus 1.
Yeah, exactly, right? This is the list of odd numbers, and what makes an odd number odd is that it's off from an even number by 1, right? This guy is 1 greater than this guy. This guy is 1 greater than this guy. This guy is 1 greater than 4. 7 is 1 greater than 6. 9 is 1 greater than 8. 11 is 1 greater than 10. So if I had to describe the list of all odd numbers algebraically, if I wanted to write down a formula for the nth odd number, I could write bn equals 2n plus 1, where n again goes from 0, 1, 2, and on. You could also write it as 2n minus 1 if you wanted to start at n equals 1, right? Do the same thing. Just being off from an even number by 1 is what makes you odd. All right. What about the last list here, Cn? If we had to
2 to the power of n?
Yeah, very good, right? These are powers of 2. This is 2 to the 0, 2 to the 1, to the 2, to the 3, to the 4, to the 5, and so on. So the nth entry in this list is 2 to the n. And again, here I'm choosing to start at 0. And then the little note is just that each of these could be written starting at 1 if we wanted, right? If we started at 1, then an would be, well, let's see, if I want to plug in n equals 1 and get 0, this I have to shift everything down by 1, right? Bn, if I replace n by n minus 1 here, that would be 2 times n minus 1 plus 1. And if you distribute that out, that becomes 2n minus 1. And Cn here, rather than being 2 to the n, would be 2 to the n minus 1. I think for many sequences, especially these particular ones I've listed here, it's convenient to start at 0. The formulas are just prettier when you do that. But the book, for whatever reason, seems to prefer starting sequences at n equals 1, which leads to the blue formulas at the bottom of the page. There's no difference between the two of them, and the textbook does jump back and forth sometimes. Just so you're aware, these problems have more than one right answer, unless you specify a starting term, right? An initial value for n. Once you do that, there's almost always a unique answer. Any questions on these guys? Okay. So we know functions have graphs, right? The graph of a function is the set of all points of the form x comma f of x, right? All the points x comma y, where y is f of x. There's nothing that can stop me from forming such a set for a sequence, because a sequence is also a function. Thus we can form the graph of the sequence and by plotting the points and comma a input comma associated output, right? So the graph of a real valued function of a real variable, f, is the set of all points, some input, comma, the output associated with that input. You take all those points together and you get the graph of f. Right? That's why if you want to know what f of 3 is, you go to x equals 3 on the x-axis, come up to the graph, and ask what's that y value? Oh, that y value is f of 3. You can do the same thing with a sequence. If I want to know, if I'm looking at the graph of a sequence and I want to know what is a5, I can go up to 5 on the n-axis, go up to that point, and the y value there would be a5. And conversely, if I give you a formula for a sequence, you can draw its graph by putting together or finding all these points. let's sketch the graph of the sequence AN given by the formula AN equals n plus 1 over n. And I should specify, I suppose, yeah, where n here will start up. Cannot start this guy at 0, right? So to do this, I'm just going to make a table, right? Just like we're back in 7th grade. When n is equal to 1, this is 1 plus 1, which is 2 over 1, that's 2. When n is equal to 2, this is 2 plus 1, which is 3 over 2, or 3 halves, 1.5. When n is equal to 3, this is 3 plus 1, which is 4 over 3, 4/3. When n is equal to 4, we have 4 plus 1 is 5, 4. When n is equal to 5, we have 5 plus 1 is 6 over 5. And 1.2. Okay, of course it keeps going. Pretty much all of the sequences we will talk about are infinite sequences, and I don't distinguish between a finite sequence and an infinite sequence. All sequences are infinite. If I want to draw this graph, you'll pay attention to the scales you pick for your inputs and outputs for your vertical axis and the horizontal axis. Your horizontal axis, your set of inputs, is now your n-axis. And the vertical axis I'll mark as y equals a. We'll call it the y-axis, but the outputs now are an rather than x's. All of these outputs live between 1 and 2. Right? The largest one is 2. This is 2, 1.5, 1.3333, 1.25, 1.2. So it wouldn't make sense for me to go 1, 2, 3, 4, 5 like on my y-axis here. Let me mark this as 1, 2. And then on my horizontal axis, I'll make it smaller. 1. Something like that. The first point on the graph, just like when you're plotting points from a regular real value function, is 1, 2. The next point on the graph is 2, 3 halves, or 2, 1.5. Again, that's about 2, 1.5, or 2, 3 halves. The next point is 3, 4/3, or 3, 1.33333, which is a little bit smaller. The next point is 4, 5/4, that's 4, 1 1/4. A little bit smaller still, but still bigger than 1. And then after that, we have 1, 1.5, 1.2. And here we go. The big difference between the graph of a sequence and the graph of a function of a real variable is that here you only have these isolated points. There is no curve connecting these points. I'm sure you could draw a curve in here, but that curve would not be the graph of a sequence anymore. That would be the graph of a function, right? A function of a real variable. In other words, there is no like point on this graph between 4 and 5. because the inputs here are only allowed to be positive whole numbers, natural numbers. So the graph, just a little note. Graph of a sequence is a collection of dots. Discrete dots. No curve. Connected curve. Now, one of the fun problems in math is, given a collection of dots, right, given the graph of a sequence, can you find the smooth curve that connects them? And that's called interpolation. And you best believe it's possible. There's a famous example in the gamma function, which we were kind of gearing up to talk about a little bit in the math thing. But that's not our game here. Our game here is not going to be, I give you a sequence, you find me the real valued function that kind of does the same thing. But I do want to find some calculus operation we can apply. Given that the graph of a sequence is just a collection of dots, there's no way to talk about continuity. Because remember, continuous means connected, right? The graph is connected, that means the function is continuous. Well, this is about as far from being continuous as you could get, right? It jumps all the time. Every time you increase the input at all, the output jumps. There's no chance for anything like continuity. And you may recall from Calc 1 that if you're not continuous, you couldn't possibly be differentiable, right? Differentiability is a harsher condition. You need to be continuous in order to be differentiable. So derivatives are straight out here. There's no way to talk about the slope of the tangent line at this point, because there's no curve here. There's nothing for the line to be tangent to. And that might make you wonder why we talk about these things in a calculus class, because the standard calculus operations don't make sense on them. There are two calculus operations, though, which we can perform. I cannot take the limit as n goes to 2, because I can't approach 2 from the left and from the right, because there isn't anything there. But if I were to continue, if you wanted to guess at what the next few dots on this curve look like, well, they're going down, 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 and they're kind of going down in this like concave up way, right? I think this would be a pretty reasonable guess. And they appear to be getting closer and closer to this horizontal line. So the first calculus operation that we're going to discuss regarding sequences is a limit, but not a limit as n goes to 2 or n goes to 5. I want to know, if you give me a sequence, do the dots start piling up on any particular horizontal line? If we were talking about a function of a real variable, we would call this an asymptote, right? This looks like a horizontal asymptote for this graph. And it's the same thing. When we find horizontal asymptotes, what we're really doing is looking for limits. Limits as the variable goes to infinity. So the calculus operation, which carries over to sequences, maybe, let me just get this in here, continuity, question mark. Differentiability, question mark. And these are both big ol' no's. Can't do anything about continuous, can't do anything about derivatives. Limits as n goes to infinity. These are what we're going to do. Can't talk about continuity because I can't take a limit anywhere else. Can't talk about differentiability because not continuous. Turns out there's one other one. So no continuous stuff, no derivative stuff. What other calculus operation might we be curious about?
I was thinking some sort of definite integral.
Yeah, there is a sense in which I can integrate this thing. Now, real quick, the normal notion of an integral here is not going to work. Yeah. So first, integration, kind of. So remember that a point is 0 dimensional, right? A point doesn't have any width. They're infinitely small. So that means I'm not going to talk about this for very long, but points are infinitely small. So I can't talk about the area under a single point. So yeah, definite integrals are going to be the thing here, but we're going to have to conceive of them quite differently because there's no way to say, oh, well, what's the area like under this point? Because this little region under this point is infinitely narrow. When you hear physicists say something is point-like, that's what they mean. They mean it's 0 dimensional. They mean it cannot bound any region of Euclidean space. So there's no area under any of these points, right? The width under each of these is 0. And because there's no curve connecting one point to the next point, there's no way to talk about the area under the curve. But if you think like Riemann sums, if I take this point and I let it define the height of some rectangle, then I can talk about the area of those rectangles, and their widths are all 1, which means that the area of, say, this rectangle would just be the height of that point, would be 4/3. The width of this next rectangle would just be the height of that point, 5/4. And when you add all those areas up, the thing you get is called a series. And we're going to talk about those. Right? This leads to series. The flavor of integral that we would be talking about would be a type 1 improper integral because it goes on and on forever, right? These dots go on and on forever to the right. And we'll get there. But before we get there, we need to understand sequences at least as well as you understand regular functions, because in order to integrate regular functions from 1 to infinity, you had to go through several classes discussing them. We're going to try to get all of that in here in one section. And we may spend more than one day on this section, just to be clear. But 11.1 is going to try to do everything with sequences that you learned to do with real functions before you had to integrate them, because 11.2 is going to talk about integrating sequences, which is series. Okay. This is a lot of concept stuff, not a lot of calculation stuff. So I just want to take a quick second to answer any questions you have about these objects. Is there anything we're wondering, or any comments anybody would like to make? Anything at all? Okay, So we said limits as n goes to infinity. That's where we're going to start, right? And we're going to need those to do this stuff. So here, the dots appear to be getting closer and closer to this horizontal line, y equals 1. So I would say that the limit of this sequence is 1, because as n gets bigger and bigger and bigger, the terms of the sequence get closer and closer and closer to 1. Remember, the terms are the outputs here, the y values. Ooh, that pen bled quite badly. Let's go through 2 sheets.
Excuse me.
Yeah.
What did you say after you wrote that like long blue paragraphs down? My internet went out and I'm on my phone now.
Oh, sorry. So after writing this down here,
Yeah.
so he
I
said
think
that, like you said, that that one of the operations we might try to consider is integration, but that integrating a sequence is a strange concept because these points are infinitely narrow, and there's no curve connecting the points. So there's no area under 1 point because that width is 0. But if you imagine that each point defines a rectangle, so I kind of plop a rectangle here, plop a rectangle here, plop a rectangle here, then each of those rectangles will have a height determined by these numbers and a width of 1. And if we start trying to add up the areas of all of those rectangles, that's very much like a type 1 improper integral. We're in some sense integrating the sequence an from 1 all the way out to infinity. That object is called a series. And in order to talk about those series, we need to first know how to take limits of sequences, because just like you define a type 1 integral as a limit of a finite integral, we're going to define these series to be limits of kind of simpler things. And those limits will be limits as n goes to infinity. There will be sequences involved every step of the way. So we're going to try to learn all the things about sequences that you know about real valued functions. And that way we can build up this concept of an integral of a sequence out of limits of sequences.
Okay, thank you.
Yeah, no problem. No. Yeah, okay. So the first stop here in the calculus direction is to define the limit of a sequence. And since this is an honors class, I'm going to give you the full banana here. But first, something a little bit more intuitive. We say that the limit as n goes to infinity of an is equal to some number, call it L, provided, or if, let's just say if, the terms of the sequence an can be made arbitrarily close to L by taking n to be sufficiently large. In plain terms, I would say that that the limit as n goes to infinity of an is equal to L if an gets closer and closer and closer and closer and closer and closer to L as n gets bigger and bigger and bigger and bigger and bigger. Right? It's a horizontal asymptote, like that blue horizontal line we saw for the sequence n plus 1 over n. So the word arbitrarily here, arbitrarily close means if you specify some closeness, right? I want the terms of the sequence to be within 0.5 of L, then I can guarantee that by finding an n big enough. And if you can do that for every closeness, there is some n that gets your sequence's terms within that closeness of L, then we say the limit as n goes to infinity of an is L. Intuitively, just think horizontal asymptote. That's it, right? L is the horizontal asymptote for the sequence. that was like this picture. Let me see if I can get both of these in here. But because this is an honors class, we're going to look at the formal definition here also. So this is our informal definition, and I'll just put the addendum here. Like L is the horizontal asymptote to the graph to y equals an. I should say y equals n. That's the intuitive definition. Now, what I was just saying is that if you want to formalize this, what we mean by arbitrarily close is that if somebody specifies a closeness factor, like say, I want the terms of an to be within 1/10 of L, then we can find a value of n that guarantees the an will be within that closeness factor. Formally, the limit as n goes to infinity, the sequence an is equal to L, means that for every positive number epsilon, for every epsilon greater than 0, there exists a natural number n, capital N. Let's say n is a natural number such that the distance from an to L will be less than epsilon, right? You'll be that close, the ans will be that close to L, as long as little n is bigger than big N. So the distance from the nth term an to the limit L, that's the absolute value of an minus L, right? If you want to find the distance between two real numbers, you subtract them and take the absolute value. We said we want the terms of the sequence an to be arbitrarily close to L. Well, epsilon is your arbitrary closeness. So I want this distance to be less than epsilon, provided I'll write it this way: little n is greater than or equal to big N. And so this is your formal definition for the limit of a sequence. And above is the informal definition. The informal definition is good enough for us, right? We won't need the formal definition to do any sort of calculation. But if you want to prove something, then you really need that formal definition. There will be a handful of times when I appeal to this formal definition in order to prove something about, say, series. I want to explore a little bit what this means. So that's the end, right? The picture if you unpack this inequality, it says negative epsilon is less than an minus L is less than positive epsilon. which means that AN is bigger than L minus epsilon and smaller than L plus epsilon. Draw my epsilon window in here. So what I want to describe here is the sequence AN converging to, that's the language we're going to use, or having the limit L. And what this definition says is that you have AN has the limit L if AN stays within this epsilon window as long as N is bigger than some capital N. So maybe A1 starts like way the fuck down here. Kind of starts creeping up, creeping up, creeping up. It might jump back down. It might come into this window. It might come out of this window. But the important thing is that once we're past N, capital N, it stays in this window. And hopefully continues getting closer and closer to this line. So we say that the limit of AN is L if for every window like this, right? If for every possible window, you can find a number N such that beyond that capital N, the terms of the sequence stay in the window. And the idea is you should think of these purple lines as shrinking in, as coming in like this. And as that happens, this N is going to get bigger and bigger. But as long as the sequence does the thing that we want it to do, right, have the terms get closer and closer and closer and closer to the blue line, then there will always be some capital N, no matter how narrow this window gets, such that all the terms of the sequence from that capital N on are stuck in that window. This is the formal definition of a limit at infinity. And it's actually the same as the formal definition for limits at infinity in real valued functions. The only difference here is that we're using n's instead of x's. So I don't care what the first finitely many terms do. These things could jump around. One of these could be up off the page. Maybe 5 of them could be right on the blue line. Maybe 10 of them bounce back and forth, up and down, up and down, up and down, in the window, out of the window, wherever the fuck you want. As long as after some cutoff point, all the terms are in the window. That's it. If you can do that for every window, even every window in the world, when epsilon is 0.000001, you can still find some capital N such that all the terms after that are in that window. If you can do that for every single positive number epsilon, then we say the limit is L. All right. Questions on the definition? Okay. And if you're ever nervous or want to kind of regroup your thinking, just again, horizontal asymptote, right? Limit of a sequence, horizontal asymptote. I don't know why this purple is bleeding so bad today. This is the same pen, same paper I always use. Get some fresh water. So I dropped the dime a second ago. I said it. This is going to be our second notion of convergence. sequences can converge or diverge. Just like type 1 improper integrals and type 2 improper integrals have a notion of convergence associated with them, sequences have a notion of convergence as well. We say the sequence AM converges to the real number L, provided the limit as n goes to infinity of an is equal to L. And again, L has to be a real number, meaning finite. If that limit is infinity or that limit does not exist, then we say that the sequence AN diverges. This is your second notion of convergence. We will also have a notion of convergence for series, which will be, again, entirely different. So I'm not a big proponent of flashcards, but this is the one place in Calc 2 where I would recommend everybody either have like a dedicated page in your notes or some flashcards where you write down the different notions of convergence and make sure you know the difference between saying type 1 integral converges and a sequence converges, especially when we get into series, because these objects kind of look similar. When we talk about series, we'll be writing things like a sub n, but there will be other symbols involved and they will have their own notion of convergence. And it is possible to get a little bit mixed up if you're not careful. So please be careful and have a dedicated page in your notes or some flashcards, and make sure that you're comfortable discussing the difference. Okay. I think it would be wise to look at some concrete examples at this point. There is more theory in 11.1, actually quite a bit more. But before I go deeper into the weeds with the theory, I just want to look at a few nice concrete examples. I'm going to start using some slightly different language here. I'm going to say investigate the convergence. So often I will give you an object which may converge or diverge. And when I say investigate the convergence, I mean, tell me everything you can tell me, right? Tell me whether the thing converges or diverges. If it converges, tell me what the thing converges to. And along the way, explain yourself, right? So you need to show steps. So I'm going to say here, investigate the convergence of the sequence, our sequence is we'll start by saying just a formula for the nth term. An is well, let's start with the one that we already did some work for, n plus 1 over n. So dn. We can do one of the other ones that we played with. How about 2 to the n? For Cn, let me take the, let's see. Plus 1, n. And any of the big things that we want to look at? Yeah. I'll call it the end. Why not? How about 2 times 1/3? I generally try to avoid these because they look like derivatives, but I'll break my rule here for this. So each one of these things is a sequence. Each one of these is a formula that spits out a list of numbers if you plug in natural numbers for n. But what I want to do is play around with their convergence. So looking at the definition above, what is it I need to do to each of these sequences to answer the question?
Like
Take the limit.
plot some of them, or yeah, limit.
Both great ideas. Yeah, so we need to take the limit. That's the definition, right? That sequence converges, is built around that limit. And the only tool that we've seen so far for investigating limits of sequences is the graph, right? Now, one of these we've already graphed. I'll just pull the graph of AN back up. Based on this graph, what can you tell me about the limit?
L equals 1.
Yeah, the limit as n goes to infinity of AN here, let's say from our graph, we believe that the limit as n goes to infinity of AN is equal to 1. So we'd say the sequence AN here converges to 1. Right? The graph is a great tool for, say, I don't want to say guessing, but estimating or getting an idea about the limit, but it's not rigorous, right? So if I want to really convince my reader that this sequence converges to 1, I need to calculate the limit using the techniques from Calc 1 that we learned. So let me put solutions, full solutions down here. This obviously is correct, right? I'm not trying to trick you or do anything mean, but I just want to be a little bit more detailed. So the limit as n goes to infinity of AN will come out to 1, but we need to have rigorous tools because sometimes, like the graph of the guy in part C here is going to be quite hard to conjure. This would be the limit as n goes to infinity of n plus 1 over n. And there's a bunch of tools from Calc 1 we could employ. We could employ L'Hopital's rule if we wanted, and I'll talk a little bit about that in a second. But there's a simpler tool. When I teach this, I call it renormalization. So you can divide top and bottom by n. And there's a third approach here that I think is actually even nicer for this one, and that's just splitting up the fraction. This is just like we did when we talked about integration, right? Sometimes it's nice to just split up fractions and handle each piece on its own. N plus 1 over n is n over n plus 1 over n. And n over n is 1. So this is the limit as n goes to infinity of 1 plus 1 over n. And you can, in your mind, imagine replacing n's by x's. We do have a theorem about that, which I'll share with you. We haven't discussed it yet, but as n goes to infinity, 1 over n will go to 0, right? It's 1 over infinity. As this bottom gets really, really, really big, 1 over that number gets really, really, really small. So this piece here goes to 0, and we get out from this just 1 plus 0, which is indeed 1. So this would constitute a complete argument, right? And the graph is good. Getting the answer right is good. But we do need complete, careful arguments, and often there will be some algebra involved here. So we were correct. I'd say the sequence AN converges to 1. In part B, in all of these, we're going to do the same thing. I take the limit as n goes to infinity. In part B, the limit as n goes to infinity of the sequence Bn is the limit as n goes to infinity of 2 to the n. As n gets bigger and bigger and bigger, 2 to the n gets bigger and bigger and bigger, right? Just like how you may have written down things like 2 to the infinity in Calc 1. You can say that this is like 2 to the infinity, which is for sure infinity. Right? If you raise 2 to a massive number, you're going to get a massive number out. And you could have made a similar argument here, saying this is 1 over infinity and that is 0. I would be okay with that. Thus, the sequence Bn diverges. For part C, the limit as n goes to infinity of Cn is the limit as n goes to infinity of the natural log of 2n plus 1 minus the natural log of n. And we've discussed that the natural log of infinity is infinity. So this piece is going to infinity because it's inside 2n plus 1 is going to infinity. And this piece is going to infinity because it's inside n is going to infinity. So this at a glance would look like infinity minus infinity. What is that?
Indetermination.
Yeah, good. That's indeterminate. So I'm going to just note here, this looks like infinity minus infinity, which is indeterminate. All right, if it was 5 minus 5 or a billion minus a billion, that would be 0, but infinity minus infinity is not 0. Infinity minus infinity is an indeterminate form, which you may recall from the section on L'Hopital's rule. L'Hopital's rule is not necessary for this problem. We're not going to use it. But we do need to recognize that infinity minus infinity isn't 0. We can't stop there. There is a nice way to attack this problem, just using algebra. I'd like to ask you, can we clean this up at all? Is there anything algebra-wise that comes to mind when you see this expression here?
ln of 2n plus 1 over n. And then you separate the fractions to 2n over n plus 1 over n.
That's exactly what I'm thinking. Yeah. So we have a rule for logarithms that says, log of one number minus log of another number is the single logarithm with the ratio inside. And then just like in part A, I can clean the expression inside up by splitting up the fraction. This would be 2 plus 1 over n inside that natural logarithm. And as before, this 1 over n piece is going to go to 0. So we're going to get out of this the natural log of 2, which is a real number. It is finite. It's about 0.69. So the sequence Cn converges to the value ln of 2. Now this last one is a little bit tricky. And we don't have the formal tools to handle it yet. So I'm going to write down what we're trying to do here and let you think about it a little bit. This is 2 times negative 1/3 to the n. We're trying to take the limit of that. The 2 is a constant, just like with all other limits, constant multiples can pop out. And I have lim n to infinity, negative 1/3 to the n.
Won't it just keep going back and forth?
This one's going to do something a little strange. So Sarah's correct in saying that the terms of this sequence will blink back and forth between being positive and negative. The negative part of this base, when raised to an integer power, will be eliminated if the power is even. Because when you square a negative number, you get a positive number, right? When you raise a negative number to the 4th power, you get a positive number, and so on. And it will be spit out anytime n is odd. Now, I can write this as negative 1 to the n over 3 to the n. And that kind of isolates the part that blinks back and forth between positive and negative. It's the negative 1 to the n, which blinks back and forth between being positive and negative. The top piece here, on its own, the limit as n goes to infinity of negative 1 to the n does not exist. So if you want to try and think of taking the limit of the top and bottom separately, we're in trouble there. The limit of the bottom, limit n to infinity 3 to the n, just like 2 to the n, is infinity. The tool you would use if this was a cosine of n or cosine of x over 3 to the x in Calc 1 would be the squeeze theorem. And there is a squeeze theorem for sequences. But because we are out of time here, I'm not going to go through that today. So what I'll do here is I will leave this by saying the tool needed is either the squeeze theorem or there's another theorem on absolute values. When n to infinity, absolute value of an, both of which will be discussed next time. So I think it would be fun for you to play around with this sequence and see if you can come up with a conjecture. It does have a limit, I'll tell you. This is a convergence sequence. And I will give you the formal tools for it next time. But I bet if you plot like the first 3 or 4 terms of this sequence, you will right away have a good guess as to what that limit is. And then to actually show it, to show the convergence formally, we will use the squeeze theorem or this theorem on limits of absolute values of sequences. They're actually very similar. But we're out of time for today, so I will go ahead and stop it here. Play around with this sequence and try to generate some other fun sequences. Next time, we're going to introduce things called recursive sequences. And we're going to go over a bunch of theorems related to sequences, which are going to be super duper important. You will have a homework set. The homework first few problems are just going to ask you to like list the first few terms of a sequence or guess at the limit of a sequence, that sort of thing. And then you can begin working those right away. The majority of the problems, though, will require some of the more advanced tools. So work a few problems between now and Wednesday. And then on Wednesday, we will begin learning the theory a little bit more deeply. All right. Okay, I'm gonna go ahead and end it here. I hope you guys have a lovely rest of your day. You need to talk to me, of course, office hours or Canvas messages, emails, all of that stuff. Take care, guys.